Hi, welcome to the latest webinar in our IoT series. My name is Natalie Pinner and I am the EMEA Field Marketing Manager at Keyfactor. I would like to introduce you to our speaker today, Guillaume Crinon, Director of IoT Business Strategy at Keyfactor. Thank you for joining us. This session is being recorded and you will automatically receive on-demand access once we finish for today. Guillaume is here to answer your questions, so submit them in the Q&A box and we will cover as many as we can right at the end. If we can't get to your questions, we'll come back to you offline and answer those directly. Finally, your feedback is important to us. Please help us improve future sessions by giving us a rating and feedback at the end. With all that covered, I'm going to hand you over to Guillaume to start the presentation. Thanks very much for joining us.
Thank you, Natalie. Hello, everybody. So my name is Guillaume. I work at Keyfactor in the IoT team, and I will entertain you today with something that is dear to my heart. So bridging the gap between the PKI, public infrastructure, which is the software that we cover at Keyfactor, with my first love when I started working, which is hardware and chips. So how can we bridge the gap between the hardware, the semiconductor, the silicon, and the PKI with certificates? So that's basically what I would like to cover today. So the agenda for these presentations, I will start by explaining why IoT devices need certificates and what they are used for. Then I will try to illustrate what is a device root of trust. It can take many forms. Then a short introduction to the PKI, public infrastructure. Then we'll look closely to X509 certificates and how they're structured, so how they're built, what's the content, and how big they are. I will go through a few examples of constraints that are put on certificates, constraints by the root of trust. I will explain that. Then I will give options for provisioning certificates in the factory. Very common options that are being used by our customers and that we cover. Then a small digression to a topic which I like very much, which is it possible to upgrade a not so secure device to a stronger root of trust, but over the air? So that's an interesting question, and I will close by explaining how EJBCA, our PKI software, can comply with every problem we'll be explaining during this presentation. So how we'll bring solutions. So I will start with IoT devices and certificates. So on this drawing, I have illustrated the whole life of an IoT device or a connected machine. So it starts at the very bottom left corner of the picture with the design. So basically when somebody starts having an idea of designing a new connected device, basically that device will materialize in hardware, which is assembling chips, silicon onto a printed circuit board. You will write firmware, so software that runs on those microcontrollers on the device. You probably sign that firmware, and then the device will go through a certification, and then it will start manufacturing in volume. And I will come back to those steps later. It will go through a final test in the factory to eliminate faulty devices or devices which do not comply with your specifications or the standards. And the device will ship to a customer, and sometimes there is a change of ownership of the device at this point. So let's say, for instance, you're in the metering business. So the blue track would be the manufacturing of a smart meter, whereas what follows on the yellow track would be the utility purchasing the smart meter and deploying it. So So that blue track belongs to the OEM and that yellow track belongs to the operator or service provider. But that's sometimes the same company with different teams in the same organization. So on that yellow track, you have to first install the device in the field, then to deploy services, maybe attach to a customer, attach the device to backends to exchange data. So if it's a smart meter, it will obviously feed some metering data to a backend to build customers. And then throughout the life of that device, you need to do some housekeeping because, of course, the firmware that you put in the device at the factory may not be perfect and you want to fix bugs. So later on, so you want to maybe update the firmware, you want to adjust some parameters based on maybe the region, based on the application, you want maybe to monitor the health of that device, so to do some monitoring here. And maybe because those devices will stay a long time in the field and business relationships may evolve, you want at some point to perform some migrations. So it can be a change of ownership, which is obviously a migration from a customer to another customer, or maybe a cloud migration if you're working with a cloud provider and for some reasons you're having a better business deal with someone else. At some point you want to migrate the fleet of devices to do that. So how do you do this securely? So basically to do all those operations, you understand that you will need secure connections between your devices and every service that is being illustrated here. And to secure those connections, you need digital certificate. That's the state-of-the-art technology. So you could do that with pre-shared keys too, but it's difficult to renew them. So whenever you can, use digital certificates to do that. And those certificates that are being used to carry those services, we call them operational certificates because they're short-lived and they must be renewed, just like the certs on your computers are being renewed on a periodical basis. But in order for those operational certificates to reach the device at all, they need to be able to prove their identity in the first place. And this is where the initial device certificate kicks in, which is the certificate that the OEM will inject at manufacturing and which will be capable to prove the genuineness of the device throughout its life and to be used very scarcely and mostly to claim an operational certificate when the device is deployed. So those initial device certificates are injected at manufacturing, either in your factory, or can be injected inside the root of trust by your silicon vendor or distributor even before you assemble the device. So we'll see those many options. So as you understand, there's not only one certificate per device, there can be many certificates per device. So I will let alone the birth certificate, which is a very special case of a very temporary certificate, which is sometimes provided by the chip vendor. But as a device manufacturer, you should care about the initial device certificate, which is the one that you inject at manufacturing. And as a device operator, you should care about operational certificates. So those certificates are short-lived and must be renewed to secure your connections. And of course, because your device is running software or firmware, that must be always signed. You should also, inside your devices, host some firmware signing verification certificates. So whereas the initial device certificate and operational certificates are absolutely unique per device, the firmware signature verification certificate is shared by every device because you assign your firmware with a private key and you're pushing the firmware to the fleet of devices. And each of these devices must be capable to check that signature key with the same certificate. Okay, so there are different kind of certs and different usage. I wanted to illustrate here that this way of thinking maps onto existing standards in the industry. IEEE 802.1AR is a standard used in the Industry 4.0 for the smart factory. So inside every PLC, for instance, you have an initial device certificate, which is an IDEV ID. And inside the factory or a complex machine, you have operational certificates called LDEV IDs, for instance. And of course, you have those firmware inside those appliances assigned. So even though the standard does not mention signing certificates, they're used on a side dish. Matter, the smart home standards specifies two certificate chains. So for the initial device certificate, that's the DAC device authentication certificate, attestation certificate, sorry, and the operational certificate when the device is deployed in the network. CITS for automotive, 64443, again for Industry 4.0. EV charging with 15118-220. They use initial device certs, operational certs, and handle firmware signing. YSUN for smart metering, which takes the same nomenclature as the IEEE 802.1AR with IDEV ID and LDEV ID. So that way of thinking certificates is deploying wider and wider into the industry across many, many verticals, more and more every year. So now back to the device. What is a root of trust on the device? So it is important to understand that behind every certificate, inside each certificate is a public key, and behind every public key is a private key. And the private key is really the equivalent in your passport to your biometric information. So that's the way that the device can prove its genuineness and authenticity. So that private key is very unique per device and should never be shared. So it's used to authenticate, sign, or share a symmetric key with another device or a server. So because it's private, it's very, very secret. It must never be leaked or shared. So other secrets can be symmetric keys, like AES keys that can be pre-shared, like on a LoRaWAN device, for instance, or during a TLS, you use symmetric keys to encrypt and authenticate the channel, because symmetric keys are faster and easier to handle than asymmetric keys, and asymmetric keys will be used to derive symmetric keys in that case. And you want to store those secrets on those private keys inside the device, and it's difficult because they must not be readable by any process other than the crypto primitives that need them. And these crypto primitives themselves must be very, very much restricted in usage to programs that can call them. So ordinary MCUs do not offer protection for those secrets, and very often they can leak them. So either not protecting the memory they are stored into so that anybody can read the memory. So that's the simplest way. And even if the memory is protected, sometimes that memory can be accessed with a few hacks, a few bugs in the chip, and even sometimes I will illustrate that with the screaming channels example on a BLE chip. Those secrets can be leaked to the RF channel. So to attack a device, you don't even need to have physical access to that device in that case. So in this example here, I've taken the example of a Bluetooth low energy system on chip, where you have on the same piece of silicon into the same package, you have the BLE radio transceiver operating at 2.4 gigahertz. And on the other side, you have the digital circuitry that runs, of course, the secrets on the baseband and all the encryption. And here in this example, when the digital side is operating, it's emitting tiny radio waves that couple to the oscillator of that transceiver, for instance, or to the power amplifier. And at a distance, really at a distance. You can see your Bluetooth channel here in blue, but as a side load, at maybe a distance of the clock frequency of that digital, you have a modulation. And inside that modulated channel, if you demodulate that precise channel with the right algorithm, you will be able to correlate things and get back to the secret keys that are being used in the chip. So those examples open back doors into servers the device took to, and can lead to wider cyber attacks of your systems. So you don't want to do that. So if you want to protect secrets into your chip, you need a solid root of trust, and that device root of trust will be the trust anchor for your device, and it can take the form of a secure element or a TPM. So TPMs are more complex secure elements that are found into our computers. It can be a microcontroller with some secure memory or trusted zone. It can be a SIM card with the IoT safe technology, and it can be a low-level software, part physically and global function, like what the company Intrinsic ID does with the design product. So I'll come to that later. So basically, that root of trust is where the device secrets will be stored and where all the crypto primitives will be safely executed, and the access to the keys will be regulated, and your private keys for initial operational certs will be there. They will only be accessed with permissions that you defined. The certificates that the device should trust, so on the server side or services, firmware signature verification certificates, of course, even though those certificates are public information, you don't want them to be replaced by some other certificates, because those certificates, although public, should not be overwritten by a malware, for instance, and symmetric keys. So root of trust, that's what the device root of trust should be, and you should make sure that it can only be accessed by only the few processes that need the device credentials and to run the cryptography. So now I will give a small introduction to what a public key infrastructure is. So we've talked about device credentials in the form of X509 certificates. And to generate those identities, X509 certificates, basically, you need to put together a framework for your organization to do that. So it's probably not the role of the business unit to deploy those identities. We always advise our customers to work hand in hand with their cybersecurity team in the IT department to do that, because those teams already know what a PKI is, and they already deploy and maintain PKI for the cybersecurity of the company. So the same tool can be used to issue device identities in volume. So that PKI idea is to provide a framework for the organization to implement those trusted identities using certificates. And basically, that PKI will allow you to manage those identities, to issue those identities, and to cancel or revoke those identities when the device is not in use anymore, or if a device goes out of business. And of course, to archive anything that happens during the process, those processes of issuing and verification, so that the system can be audited and made compliant with standards and regulations. So that PKI will be articulated around a few different things. It starts with a policy, and the policy is what? You answer the question what my PKI should look like. What are my identities, and what is their format? What should they comply with? You will define the certificate policy, basically, and that gives the whole rules around your public infrastructure, and which will explain your cybersecurity team what you want to do and what you want to cover in that PKI. Then it will be procedures, where you will describe how you execute to the policy, and that will be described in certificate practice statements usually. So basically, you will explain to the inside the document how you will set forth in the policy what ceremonies, for instance, you have to do when starting a new CA, or what you want to do there. Roles, because you have human beings behind the PKI, so you have to design role-based access control. So who does what, who can do what, and who cannot do what, who can access to which branch of the PKI for which products. So here you can segment between product lines and between different people. You can set, backup. So if my admin is on a leave of absence, who can take over, or do I need 2 or 3 or more people to do that action for the sake of security in the company? Because you should not underestimate the importance of the digital identity for your company. It's like tagging a logo inside a chip. So you really commit with the blood of your company. So you should be very careful about the policies, procedures, and the rules, who does what. And then you have the hardware and software side of things, which is where and how you implement the PKI really in real. So do you need a HSM, so hardware security modules to host your private keys for your CAs? And will you maintain your root offline? Will you segment between the different functions of the PKI? And for instance, what's your SLA, service level agreement? What's the resilience of your implementation? So all that should be defined in these PKI. And last, about the PKI, a PKI can be segmented into 3 functions. So again, I will take the analogy with the passport, which everybody knows. So the RA for registration authority, which is the desk where a device will enroll and will present its identity and prove its genuineness to claim a certificate. So it's like, for instance, the desk where when you go to have your passport created, where you will enroll, prove your identity, and state your name and address and everything. The CA is the certificate authority, which takes the enrollment demand from an array and issues a certificate. So here it's the authority that will issue the passport and sign the passport. So that's the government office that will do that. And then the VA, the validation authority, is a desk where everybody looking at the passport can go to this service and ask whether the passport is valid or not. So same for a certificate. Imagine a server receiving a device certificate. That device wants to connect. The device will exhibit a certificate. The server can go to a VA, validation authority, and ask, is that certificate genuine, or has it been revoked in the past? Now let's look at the structure of an X509 certificate. So basically, it's a file, it's a document, and the certificate in a PKI tree is either a node or a leaf, where at the top you have a root, CA, which can branch into sub-CAs. Issuing CAs are usually the ones, we call them the working CAs for the IoT world, because they are the ones who will generate device identities in the factory, for instance, or for the factory, or generate device certificates, operational device certificates during the life of the device. And you can have branches that will take care of firmware signing keys and verification certificates. So basically, inside a certificate is the device data. So basically, what is the device? Is there a certificate? What is the certificate serial number? Who issued the certificates? Then there's validity, like on a passport, valid not before, not after, and these are dates. Then there's a public key in there, which is very specific to the device, with a hidden private key behind, which is not in the certificate, but hidden behind the certificate. And that private public key pair is basically the biometric information of the device. This is how the device proves its authenticity and genuineness. There's a signature part, so the authority who has checked the authenticity of the device, that the device credentials match with what the device claims it is, and signed the certificate, so that authority has a signature here, which can be checked. A few usage and extensions that explain what the certificate can be used for. So here, encryption or digital signature, just like an ID document. So you have a driving license, it's valid to drive cars, and you have a passport, it's valid to travel, but you cannot use one for the other. And in the end, the VA validation information access. So where can you check the validity of that certificate? What is the URL that you will point the recipient of that certificate so that it can check the validity of that certificate? And if we look closer at the content of this file, we can estimate the size of the certificate it's signed. So usually the end entity data, which is the subject of the certificate, can be reduced to a few tens of bytes to a few hundreds of bytes. The validity date is something like 30 bytes, more or less. The public key really depends on the technology cryptography used in the PKI. So elliptic curves P256, which is a common choice for IoT, yields 64 bytes for the public key, whereas RSA, the equivalent of P256 for RSA is 3072, is 388 bytes, so much larger. Same for the signature, a few bytes to describe usage and extensions. VA validation access, again, 100 bytes. And the private key is 32 bytes in the case of ECC, and 384 in the case of RSA. But again, it's not inside certificate, so it's behind. So first remark, you can notice that the size of an X509 certificate isn't fixed. So for an RSA certificate, expect something like 1.2 kilobytes. So it's not cheap inside a device or inside a memory, or even if you're transacting those certs across a constrained radio channel. For elliptic curve 256, it's more like 300 bytes, so which is not much for wide bandwidth channels, but which can be challenging if you're discussing over a LoRaWAN, for instance. You won't have that bandwidth to do it. Those files are encoded, so with the abstract syntax notation, ASM.1, encoded. You will find them encoded two ways. So most efficient way is the DR encoding, so distinguished encoding rules, binary. It's the most compact, and sometimes you can find them on your PC, for instance, in your web browser, in the form of PEM for privacy enhanced mail encoding, and it's base 64 text encoding. So basically, at least 33% more larger in size than in binary that way. And of course, the more extensions you add, the larger the file will be, the certificate will be. I would like to illustrate with a few restrictions on that some root of trust put on X509 format. So basically, you understand that an X509 certificate can grow to much larger even than 1.2 kilobytes, as I mentioned it. So if you add more extensions, if you have more complex URLs to access to validation certificates, you can have different usage for certificates. You can even grow to not far from 10 kilobytes sometimes in size. So when you want to store those certificates into your root of trust, you will have to be very careful, because not all the root of trust or not all the services allow for an unlimited size of the certificate. So I've taken a few examples here from the industry. So I'll start with one of the most popular secure elements in the industry, but also the most constrained. So that's microchips ATACC 608 secure elements. So whereas on ECC certificate, we have evaluated the size of an ECC certificate to be around 300 bytes. That secure element, for instance, allocates only 72 bytes for the certificate, which means that it's just not possible to store the certificate as is. And Microchip defines a specific compression scheme to achieve that. So basically, they create dependencies. So the serial number of the certificate can be a hash of the public key of the certificate and the validity dates. The validity dates themselves have a resolution which discards minutes and seconds, and for the end validity, it's only in years. So you reduce from 30 bytes to a few bytes, under 10 bytes. And extensions are in a strict order, so it will also simplify a lot the encoding of the certificate, because the parser will expect to see every field at a very precise place. So not allowing any mixing in the ordering. The ST safe from ST Micro, for instance, the serial number must be exactly 11 bytes long, and it must start with those bytes 0209. Silicon Labs has a secure vault with a personalization service, and they only allow distinguished name personalization, and the common name must be 30 character, and starting with a 64-bit UID of the device and end with those strings. So you see, every root of trust silicon vendor, for reasons that may be legacy sometimes, because they're just refurbishing all silicon to a new market, and they have those constraints, and they're trying to find clever ways to adapt the technology to what they have and to what's available. And it works. It works very, very nice. So the idea here is knowing those constraints and knowing the immense choice that you have when you build certificates. How can we reconciliate both worlds, a world of constraints from the hardware and a world of software from the PKI side? So basically, that's the idea behind the bring your own root of trust paradigm, where we understand at Keyfactor that when you build IoT devices, your root of trust can be very diverse. So everything I mentioned, that factory provisioning is always difficult, and we're trying to simplify that. And in that purpose, we've designed that program to allow any OEM to source whatever silicon they prefer, and we don't give constraints, and we don't ban any secure element or any personalization scheme in that regard. And at the same time, we still allow them to issue device certificates to comply with the standards they're designing for. So there are two possibilities. I mentioned that to do factory provisioning for your certificates. So the IoT identity provisioning can happen before you assemble the product in your factory. So some silicon vendors offer the possibility for you to inject for you a certificate into the secure element before it is shipped to your factory. And that can be very convenient because in this case, you don't have to care about managing the PKI in real time. You can outsource manufacturing to a contract manufacturer very easily because they give you a unique part number that really points to the device with certificates that come from your PKI. And for that usage, we're defining with those silicon vendors a process so that you can attach the working CA, which they have in their own factory. You can attach that to your PKI so that when devices will exhibit their initial device certificate later in the field, those certificates can be traced back to your PKI and not to the silicon vendors. So it's very important to understand that it's a higher level of security. Sometimes it is difficult to do the silicon vendor trick just because imagine you're manufacturing 10 different products, and for those 10 different products you have the same hardware, maybe Wi-Fi module platform. So in the way you manufacture devices, you start by manufacturing a small Wi-Fi module that can go then into 10 different products. And when you manufacture the Wi-Fi module, you don't know in which product it will end. So that you cannot tell your silicon vendor, put in that Wi-Fi module a certificate for, I don't know, washing machines, or a certificate for TVs, or a certificate for PLC. In which case, you cannot use them and you have to buy blank chips and you have to do the certificate generation and injection yourself during manufacturing. So we have solutions for that, but that requires calling the PKI from the factory. And depending on what you want to do, whether you outsource or not, the architecture will be slightly different because you don't want to open access to your PKI to the outside without strictly restricting access to computers that you trust, on processes that you trust. So we have ways to cope with that. An interesting question. So imagine you have devices and they've been designed maybe 5 years ago, and the certificate was not a big deal at the time. And now you're understanding that you would like to give them a stronger identity. So how do you possibly upgrade those devices over the year and in the field and retrofit them with a stronger identity in the form of the certificate? So basically, inside those devices, you will need to have secure storage. Of course, we discussed that. A true random number generator. So I have not touched that point, but random numbers are so important in the root of trust because in cryptography, the better the randomness of a number, the more difficult to crack or to hack the cryptography. So in that device that you're grading, you also want to have a very good, maybe better than what you have random number generation. Of course, you need at least one unique private and public key pair. You need to have some crypto primitive which can resist to attacks. Stacks like DTLS that can, or MTLS, MDTLS that can resist to side channel attacks as well. And of course, state-of-the-art PKI to generate your certificates and be able to manage them. And at the same time, if you're retrofitting a device in the field, you could do that with unitary firmware upgrades. So assembling unique firmware is one per device. So if you have 10,000 devices, assembling 10,000 firmwares, each firmware with a unique identity, a unique certificate, maybe encapsulation or private key, something. But that would be very difficult to put in place in practice because unitary firmware updates are so cumbersome. So how about a broadcast solution? So you broadcast the same software to all the devices and the magic happens. So what would that firmware stack look like? So for instance, I mentioned intrinsic ID in my introduction. So they have a very, very interesting piece of firmware, which is basically capable to harvest RAM cells, discrepancies in the RAM cells, to derive a unique private key for the device. So that the device receiving that software, that firmware, you can send that to 10,000 devices. They will all wake up with their own unique private key and public key pair. And then you can add a layer of a good TLS software on that. So that if you have pre-existing devices, you can broadcast the software update to those devices. They wake up with unique private key pairs. They can assemble a certificate request, get a certificate, a unique certificate from a PKI, reset again, and now restart with certificate-based authentication to your service. So yes, it is possible. EJBCA is the PKI software from Keyfactor, and it's been designed for the world of IT to start with, but we've adapted it to the world of IoT, and it is so flexible that all the constraints we covered in the root of trust, they all can be addressed in that software. So in the format of the certificate, in the scalability of the solution, if you need to issue certificates, it's one thing to be able to assemble a certificate with a very constrained format by hand, manually, but how about automating the task and doing that in volume? So EJBCA allows that with, of course, certificate profile forms that will allow you to apply certificate profiles to fleets of different certificates and entity profiles. And for everything which is not covered by those two features in the GUI, we have very powerful APIs to help you automate the issuance of certs in volume and with all the constraints that do exist in the industry. And believe me, we're watching them continuously, and we work with the silicon vendors to make sure that we continuously comply with the any hardware root of trust that sells in the market. So EJBCA is a very powerful PKI software. You can segment into CA, VA, RA. It's unlimited in the number of certs. On CA, you can create. You have the support for all root of trust and certificate lifecycle management, HSMs. It's common criteria certified. You can extend it easily with all the protocol for enrollment, and you can share the usage between IT, IoT with the same license. It's very scalable. And I think that covers my presentation for today. Natalie, can I ask you to...
Of course, thanks, Guillaume. We recently released a research report on IoT security, which is available to download on our website. You can either scan the QR code here, or it is available in the attachments section. If you're interested in learning more about the findings of that report, you can join us on Thursday this week. And if you're watching on demand, still scan, still link, because you can watch on demand as well. And with that, I think we have run out of time for questions, but thank you very much for joining us. Thanks, Guillaume.
Thank you, everyone. Thank you, Natalie. Thank you, everyone.